Hello everyone, welcome you to CSE 350 Digital Electronics and Pulse Techniques. In this video, we will discuss about diode transistor logic or DTL NAND gate. We all know how NAND gate logic works. In this truth table, you can see when all the inputs are high and only then the output is low. And in all the other cases, the output is high. We also know that a NAND gate is equivalent to a AND gate connected in series with an inverter. So this idea of combining an AND gate and an inverter to create an AND gate have been utilized in this circuit. We can clearly see two divisions in this circuit. The portion in the left hand is actually a diode logic AND gate, and we have already studied this. And the right hand part of this DTL NAND gate can be thought of as an RTL inverter, and we have also studied this in our previous lecture. The nodes A, B, C are the input of diode logic AND gate, and the output node of DL AND gate is the P node. And the input node of the RTL inverter is this node, the base node of transistor T, and the output of the RTL inverter is the Y node. So the output of DL AND gate is connected to the input of RTL inverter using two back-to-back connected diode like this diagram. 3 input AND gate is connected through two back-to-back connected diode to the input of RTL inverter. Now we will see the basic operation of DTL NAND gate for different input combinations. As this is a 3-input NAND gate, there are total 8 different input combinations possible, but all the input combinations can be divided into two parts using the fact that the output is high when at least one of the inputs is low, and the output is low when all the inputs are high. So we have divided input combinations into two groups when at least one of the inputs is low and when all the inputs are high. Now consider the case that at least one of the input is low. In this circuit, we will consider the logic level corresponding, the voltage level corresponding to logic level high to be the same as VCC, that is 5 volt, and the voltage level corresponding to logic level low to be 0.2 volt. Okay, now assume that the voltage of the node A is 5 volt, that is high. The node voltage of B is 0.2 and the node voltage of C to be 5 volt. So the inputs A and C are high and only the input of node B is low. Now we will analyze the circuit. As the node B is low, that is the connected voltage is 0.2, the diode DB can be turned on and there can be a current from VCC through node P through diode DB to the node B. The diode DA and the diode DC cannot turn on because if the diode DA was turned on, the node voltage of this node would be 0.7 volt higher than node voltage of the node A, that is 5.7 volt, and there is no way a current can pass from 5 volt to 5.7 volt in the positive direction. So the diode DA and the diode DC they will be in cutoff, or they will be turned off. Now what happens to the diode D1, D2 and the transistor T? They are also in cutoff. So the diode D1, D2 and the transistor T, they are in cutoff, so they are off. So why are the diodes D1, D2 and the transistor T off? Because if they were on, they will create a contradiction, and we will see what is the contradiction. So the diode DB is on, so there is a 0.7 volt voltage drop across the dB diode. So the node voltage of P would be 0.7 volt higher than the node voltage of B. So the node voltage of P would be 0.9 volt. Now suppose that the diode D1 is on, so there will be 0.7 volt voltage drop across the diode D1. So what will be the node voltage of this node? The node voltage of this node will be 0.7 volt lower than 0.9, that is 0.2 volt. And also assume that the diode D2 is on, so there will also be a 0.7 volt voltage drop across the diode D2. So what will be the node voltage of this node? The node voltage of this node will be 0.7 volt lower than 0.2, so it will be negative 0.5 volt. Now to turn on a transistor, we need at least a positive voltage across the base emitter junction. So the base emitter voltage must be positive to turn on this transistor, but the voltage of base node, we have calculated this to be negative 0.5, and the node voltage of emitter node is 0. So the base emitter voltage for our case is negative 0.5. So the transistor T cannot turn on. When at least one of the input is low, in our case only the input of node B is low, and in all other such cases when at least one of the input is low, the analysis is very similar to this. Now we will calculate the value of Vp, the node voltage of P, and the node voltage of output node Y for this case. And we have already calculated the node voltage of P, and the node voltage of P is 0.9. Now we'll calculate the output voltage. Okay, so the transistor T is in cutoff. So as the transistor T is in cutoff, all the currents, the base current, the emitter current, and the collector current will be 0. So in this case we need only the collector current. The collector current is 0, so this is the collector current, and as the collector current is 0, what will be the node voltage? The node voltage will be the same as VCC. So the output voltage will be 5 volt. Now we will consider the case when all the inputs are high. Now all the inputs are high, so the node voltage of all the inputs are 5 volt, and using our previous argument we can show that the diode DA, the diode DB, and the diode DC, they will be off. So the only way for the current to flow from VCC is through the diodes D1, D2, and through the transistor T. So they all will be turned on. And we will assume that the transistor T operates in saturation, and in later part of this video we will show that why this assumption is valid. So let us analyze the circuit. As the transistor T is in saturation, the base emitter voltage will be 0.8 volt. So the emitter voltage is 0 because it is grounded, so the voltage of base node will be 0.8 volt. So this is the base node. The voltage of base node will be 0.8 volt. And also you know that when a transistor is in saturation, the collector emitter voltage is 0.2 volt. So the node voltage of collector node, in this case the collector node is also the output node, its voltage will be 0.2 volt. So we have already got the output voltage. The output voltage will be 0.2. Now as the diode D2 is turned on, there will be 0.7 volt voltage drop across this diode. So the node voltage of this node will be 0.7 volt higher than 0.8, that is 1.5. And similarly the diode G1 is turned on, so there will be 0.7 volt voltage drop across this diode. So the voltage of this node or the P node will be 0.7 volt higher than 1.5, that is 2.2 volt. Okay, so the node voltage of P will be 2.2 volt. And as we have calculated the node voltage of P, this whole node is the P node, we can actually calculate the value of this current. This current is the same current that flows through the diode D1, D2, as no current goes through the diodes, input diodes DA, DB, and DC. So this current and the current that flows through the diodes is the same. So it can denote this as I1, and the value of I1 will be the voltage difference across the resistor R, that is VCC minus VP divided by R, and for our case the value of I1 will be 0.56 milliampere. Now we will see that if we choose an appropriate beta value, then our assumption that the transistor T operates in saturation mode will be valid. Now consider the input combination when the transistor T operates in saturation, that is all the inputs are high, and then the input diodes are turned off. The diode D1, D2, they are turned on, and we also know all the node voltages. The node voltage of P is 2.2 volt, and the output voltage is 0.2 volt. Now we will calculate the collector current. The collector current IC equals, this is the collector current. So the collector current can be calculated using the voltage difference across RC resistance, that is VCC minus VY divided by the resistance RC. So the value of collector current will be 2.182 milliampere. Now we will have to calculate the base current. So how we will calculate base current? We will apply KCL to this node. If we apply KCL to this node, we will get the current I1 comes towards this node. So I1 equals the current IB and the current I2. They go outward from this node. So I1 equals IB plus I2. We have already calculated I1 in our in previous part of this video. The value of I1 was 0.56. We have to calculate IB, and what is the value of I2? Okay, I2 current flows through the RB resistance, and what is the voltage across this RB resistance? We already know the node voltage of this node. We have assumed the transistor T operates in saturation, so the node voltage of this node will be 0.8 volt. So I2 will be 0.8 minus the voltage of this node, that is 0, divided by RB resistance. So we can calculate the value of IB to be 0.4 milliampere. Now, as the transistor T operates in saturation, the ratio of IB and the ratio of IC and IB must be less than beta. In our case, the value of IC is 2.182, the value of IB is 0.4, so 5.46 must be less than beta. So if we choose the beta value of the transistor to be higher than 5.46, this inequality will be correct, and our assumption will create no contradiction. So the minimum value of beta that we can choose is 5.46. So thank you. In the next video, we will calculate the noise margin of DTL NAND circuit.